Welcome to this explainer. Today, we're stepping right into a microscopic arena to witness an absolutely epic battle between elements. We often think of metals as these solid, unchanging, boring materials, right? But on an atomic level, there is a fierce competition going on. We are looking at the intense and honestly sometimes violent world of displacement reactions.
Okay, let's dive into this. What exactly happens when two metals are forced into the same space and have to compete for resources? While chemistry has a very strict hierarchy, there is no sharing, and there are absolutely no ties. When metals compete, one asserts its dominance, and the other just gets kicked to the curb. It's a really fascinating chemical power struggle, and by the end of this explainer, you'll be able to predict exactly who wins every single time.
So here is our roadmap for today. We'll start with the law of displacement, then look at the reactivity hierarchy and the electron tug-of-war. After that, we'll check out some colorful chemical evidence, look into real-world metal extraction, and finally wrap up with exactly how to ace your chemistry exam. All right, Section 1, the law of displacement. Let's lay down the fundamental rule for this microscopic competition.
So the crucial point is this. A displacement reaction occurs when a more reactive metal replaces a less reactive metal from its compound or solution. Think of it as the ultimate bully role of chemistry. The stronger, more reactive metal just walks up to a compound, shoves the weaker metal out of the way, and takes its place. And the weaker metal, it's just left all by itself.
Let's look at how this actually plays out in a chemical equation. Our general rule is pretty simple. A more reactive metal plus a less reactive metal compound yields a brand new compound plus that less reactive metal on its own. A classic example is dropping pure zinc into copper sulfate. Because zinc is the more reactive metal, it totally displaces the copper. The result? Zinc pairs up with a sulfate to create zinc sulfate, and copper gets completely kicked out. Left is just pure unattached copper. But that raises a big question. How do we actually know zinc is stronger than copper? To predict the winner of these chemical battles, we need the official ranking of the metals, which brings us to Section 2, the reactivity hierarchy. Enter the reactivity series. This is ordered from the absolute most reactive at the top all the way down to the least reactive at the bottom. If you're a focused learner looking for the ultimate cheat sheet, honestly, you'll want to remember this. To memorize it, we have this brilliant visual mnemonic. Please stop calling me a careless zebra. Instead, try learning how copper saves gold. The first letter of each word perfectly matches the elements. Potassium at the very top, followed by sodium, calcium, magnesium, aluminum, carbon, zinc, iron, tin, lead, hydrogen, copper, silver, and sitting comfortably at the absolute bottom, gold. And this brings us to the golden rule of displacement. A metal can only displace another metal if it sits higher up on that reactivity series list. A weaker metal simply cannot punch above its weight class. So if you try to reverse our earlier experiment and drop pure copper into zinc sulfate, absolutely nothing happens. Copper is way below zinc on the list, so there is no reaction. The bully only wins if it's, well, actually the stronger metal. Let's move on and see how this builds, transitioning from what happens to exactly why it happens. Section 3, the electron tug-of-war. On an atomic level, displacement is essentially a literal tug-of-war for electrons. You see, more reactive metals lose electrons super easily. They desperately want to form positive ions. So when zinc is added to our solution, it undergoes oxidation, which simply means the loss of electrons. It gives up 2 electrons to become a zinc ion. Meanwhile, the copper ions in the compound undergo reduction, which is the gain of electrons. Those copper ions grab the 2 discarded electrons to become pure copper metal. We can perfectly summarize all this atomic drama using an ionic equation. Zn plus Cu2 plus yields Zn2 plus Cu. But wait, notice someone missing? The sulfate ions are completely omitted from this equation. Why? Because they are literally just bystanders. They do not take part in the electron transfer at all. The entire conflict, the whole shebang, is strictly between the zinc and the copper. Now, atoms are way too small to see with the naked eye. So how do we know this tug-of-war is actually happening? Let's check out Section 4, colorful chemical evidence. And this brilliantly illustrates how knowing these specific colors turns abstract science into highly visible transformations right in the lab. Copper sulfate is this vibrant, beautiful blue. Iron 2 sulfate is a pale green. Meanwhile, zinc sulfate, magnesium sulfate, and silver nitrate,
totally colorless. When a displacement reaction happens, the solution physically changes color right in front of you as the old compound is destroyed and the new one takes its place.
Let's look at the results of a real practical experiment where we test different metals against that blue copper sulfate. When we drop in magnesium, the reaction is incredibly vigorous. The blue color disappears rapidly, brown copper metal instantly forms, and the magnesium just dissolves away. Zinc yields a fast reaction with the exact same visual results. Iron gives a much slower reaction, slowly turning that blue solution a pale green as iron sulfate forms. But what happens when we drop pure copper into the copper sulfate? Absolutely no change. This data perfectly proves that our reactivity series is very real. The higher the metal on the list, the faster and more violent the displacement.
Okay, it's time to step out of the classroom for Section 5, Real-World Metal Extraction, because industries actually weaponize this exact chemical hierarchy. Now, what's really interesting here is this higher-level application, the thermite reaction. Here, we are looking at iron oxide reacting with pure aluminium. Because aluminium sits higher on the reactivity series than iron, it aggressively bullies the iron away from the oxygen. The aluminium displaces the iron, forming aluminum oxide and kicking out pure iron in a massively energetic release. And when I say energetic, I mean this reaction is incredibly exothermic. It produces immense amounts of heat. Because of this displacement reaction, the iron that gets kicked out is actually produced in a molten, totally liquid state. Engineers use this specific reaction for railway track welding. By triggering this displacement right there on the tracks, that molten iron perfectly welds the heavy steel rails together. It is just a stunning example of microscopic rules doing serious heavy lifting out in the real world.
All right, let's bring it all home with Section 6, Acing Your Chemistry Exam. This is designed specifically to help you take everything we've talked about and completely crush your next test. If you are ever faced with a displacement question on an exam, just run it through this foolproof 4-step algorithm. Step 1, find both metals in your freshly memorized reactivity series. Step 2, decide which metal is more reactive. Step 3, if the metal being added is higher on the list, boom, a reaction occurs. Write down the new compound, the displaced metal, and whatever expected color changes there are. Step 4, if the added metal is lower on the list, don't overthink it, just confidently write no reaction and move on.
But please, be careful to avoid these super common traps that cost students points all the time. First, never assume that just because two chemicals are mixed together, a reaction automatically happens. Remember the golden rule. Second, memorize those color changes. If zinc displaces copper, you have to state that the blue solution becomes colorless and a brown coating appears. Lastly, always check your ionic charges when writing formulas. Knowing that copper sulfate is CuSO4, for instance, ensures your final equations are perfectly balanced. This summary matrix perfectly structures everything we've learned today. Look at magnesium, total king of the hill on this specific list. It displaces the metals in copper, iron, and zinc sulfates. Zinc can only displace copper and iron. Iron is even weaker, only managing to displace copper, and then we have copper and silver way down at the bottom, which react with absolutely nothing on this table. It's so perfectly predictable. Which brings us to the end of our explainer. The laws of reactivity, they aren't just stuck in textbooks. They genuinely govern the physical world we interact with every single day. So I'll leave you with this thought. Look around you right now. Whether it's the electronics on your desk, the jewelry you might be wearing, or the actual pipes in your walls, which of the metals in your room are slowly losing the chemical tug of war? Keep observing, keep questioning, and we will see you in the next explainer.